Hello everyone, we are going to talk about relations today in mathematics, and this is also the chapter 1 for class 12. So to study about relation we need basic knowledge of what is called a set, and we represent a set by capital letter A, B, C. All these are set. This is my finite set with 4 elements. This is also a finite set with all the alphabetics A, B, C, D up to F. Now this is an infinite set of even numbers 2, 4, 6 up to so on. And the another form of a set is set builder form, where we write my set D is such that all those x which are equals to 2 into some n, where my n goes from 1 to 10. This can be written like this: for n equals to 1, x will be 2, n equals to 2, x will be 4, n equals to 3, and so on up to 20. This is my set. Now after set we studied product of two sets, that is A cross B, product of two sets. This is usually given by A cross B equals to a coordinate pair AB, such that my A will belong to my first set and my second coordinate B will belong to my second set, that is B itself. Okay, in same way I can make A cross A, which will be a coordinate pair itself, where both of my coordinates or elements will be from the same set A. For example, we have A equals to 1, 2, 3, finite set. Then A cross A will be what? First element, second element also from A. So second element can be 1 itself. That's why we have 1, 1 coordinate pair, because 1 A equals to 1, B equals to 1 here. A equals to 1, B equals to 2 here. A equals to 1, B equals to 3 here. After this we don't have any other choice instead to take A equals to 2, and this is how we define A cross A. And about the cardinality, this is the representation of cardinality, that is number of elements. Number of elements in product of two sets is generally number of elements in first set multiplied by number of elements in second set. In the same way, we can have A cross A. Cardinality of A cross A will be cardinality of A into cardinality of A again. That will give me 9, because here cardinality of A equals to 3. So this was the basic knowledge of set theory which I need to study my relation. Okay, next, what we can do about a relation now. What we can say about a relation? The most basic definition of a relation in my terms will be a relation R. Usually we denote it by capital R. A relation R is nothing but a subset. A relation R is subset of product of two sets A cross B. And instead of studying this A cross B, most probably through whole of the chapter we will be studying R as a subset of A cross A. This is the most basic definition of a relation. A relation is nothing but a subset. Now if we go to A cross A, my A cross A was what? 1, 1, 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3, then 3, 1, 3, 2, and 3, 3. This was my A cross A. Now my relation R, I have a relation R which should be subset of A cross A. We put equal also because we will study that this relation can be the whole A cross A also. Okay, now R equals to 1, 1, 2, 2, 3, 3. I choose this equals to my R. Now this is a relation. Is this a relation? Of course, because this is subset of A cross A. But how to define a relation? That is the thing. How to define a relation so that we get these elements. Now this thing is clear that relation will also be a set. Elements of a relation will be of the form coordinate pair, because A cross A is of this form, so subset also will be of this form. So what only remains to understand that how to define a relation, because we know how relation will look like. It will be a set having a coordinate pair as its elements. Now suppose we have a group of boys as a set A. Clear? My set A is a group of boys. Now I will define a relation R equals to, this will be a ordered pair like this. These will be those boys which are in the set A. A is a boy in set A, B is a boy in set A. I need A comma B, means A related with B. In what manner? This is how I define my relation, that A is brother of B. Simple. This is a relation. How? Because I can find two boys which may be brothers of each other. So then we say that my A is related to B, because A is brother of B. So A is related to B. Clear? So this is my definition for this relation. I will have a set A, then I'll find out what is the definition for relation, which will give me set like this. Now this is my definition. Clear? A can be Ram, Shyam, and one more, that is Jack. Clear? Now if Ram and Shyam are brother, then Ram is related to Shyam with this relation. Clear? If my set is only this, Ram, Shyam and Jack, this is my A only with 3 elements, then how will I find this R? R is this relation. This is the condition which these 2 elements needs to satisfy. So here my R only will be a singleton, Ram, comma, Shyam. Because these 2 are brothers, only these 2 boys satisfy this condition, so they can lie in this relation. There can be many more. We will give their names in brackets and make a coordinate pair. Clear? So this was a basic example of a relation. Now relation can also be given in mathematical terms, like a condition, a equation that needs to be satisfied. We take another example. We suppose B is my set with 1, 2, 3, 4, 5, 6, 7, 8 elements. Now I define my relation R as all those elements AB. Of course A comma B will both belongs to A. Now here my set is B. Now I can write my both the elements will belong to the set B, because in this term my R will be subset of what? B cross B. Okay. So what is the condition? Condition is that A plus B should be equals to 10. This is how I define my relation. Now what this relation will contain? All those coordinate pairs A comma B which satisfy this condition. So 1, no, I cannot pair 1 with any element, but I can pair my 2 with 8, because 2 plus 8 will be 10. And remember that 8 comma 2 also satisfy this condition, because 2 plus 8 is 10, 8 plus 2 is also 10, and in B cross B there will be 2 cross 8, 2 comma 8 and 8 comma 2, both will be different element. So I can write 3, 7, 7, 3, 4, 6, 6, 4, and all this. Last element will be 5, 5, this much. This will be my relation. Condition which defines my relation, output, set, elements as coordinate pair. This is my relation. Okay. Now my relation R comes to be 2, 8. If I look on the previous page, my relation was this. This was the set that I got after applying the condition that A plus B equals to 10, where A comma B belongs to the set B, and B was 1, 2, 3, 4, 5, 6, 7, 8. Now I call this my relation 1, because this is not necessary that we will only have one relation on a set. We can have more than one relation. R2, my relation 2, I define this as coordinate pair AB such that A is strictly less than or equal to B, where both A comma B belongs to B. We can quickly find out the relationship that 1, 1 is an element, 1, 2, 1, 3, and 1, 4, 1, 5 up to 1, 8. I'll have every element. Now with 2, I'll have 2, 2, because the equality is also there. 2, 3 as well. 2 is less than 3, and so on up to 8, and then 3, 3, 3, 4, and then 4, 4, 4, 5. Like this we can find out our relation 2 that I call R2. We can define many more relations. Now if I look at R2, I don't have pair 2, 3, 2 does not belongs to R2, this relation. Now what do I say? 3, 2 does not belongs to R2. That means 3 is not related to 2 from this relation. But if I have 3, 2 in some other relation, then we'll call that 3 is related to 2. Like here, 2 related to 3. This implies that my 2 is related to 3 with relation R2. Okay, from R1 we can see that 2 is related to 8, 8 is related to 2, and so on. So this is just a notation that 2 is related to 3, or how we can say that an element A is related to B, where both A and B belongs to the relation. Okay, now I have two simple definitions related to my relation. One is empty relation. Empty relation. If the set R1, R2 both have elements, but there might be a relation on this set B which will give me an empty set. Like if I define my relation R of ordered pair AB such that A plus B equals to say 100, where A comma B both belongs to the set B, which is written here. Now no two elements from B can satisfy this condition. There are no elements. So let us take it R3, because R1 relation, R2 relation we are done. We take it R3. So clearly R3 is 5. This is an empty set. I don't have any element A comma B satisfying this condition. So this is my empty relation. If there is no element in R3, then I'll call it as empty relation. And mind it, definition of relation was what? Subset of A cross A, or in this case we will say subset of B cross B. So remember that phi is always subset of every set. Clear? Now next is my universal relation. What is universal relation? There might be some relation which carry out all of these elements from B cross B. Like if I have some R4 relation which is equals to B cross B, then my R4 will be universal relation, because every element of B cross B will be in R4, relation 4. Clear? Because by the set of relation we already have R4 will be subset of B cross B, and because we are defining my universal relation, then this means that every ordered pair A comma B in B cross B will also belongs to, this implies my A comma B will also belongs to R4, and this makes that R4 contains B cross B, and from here and here we can say that R4 equals to B cross B. So what could be that relation which defines an universal relation, which defines a universal relation on the set B? We can think of something like a trivial kind of relationship, very trivial relationship. We can form that A comma B such that my A is less than or equal to 8 and my B is also less than or equal to 8. Yeah, and A comma B both belongs to B. This is my relation. Because why I don't keep these positive, A and B positive here? Mind it, I don't need to write that A is positive or greater than 0 or B is positive or greater than 0, because A comma B belongs to B, then A comma B at the minimum point will be 1. Clear? So A, B will already be positive because they are from B, and B is from 1, 2, 3, 4 up to 8. So this will give me a universal relation because it contains complete B cross B. It will contain B cross B completely. Okay, now we will talk about equivalence relation. What do we mean by an equivalence relation? Before studying about equivalence relation, we need to understand that equivalence relation, this will also be a relation, namely R, defining by some condition. Equivalence relation constitutes of 3 conditions. We need 3 conditions to be satisfied in order to say that the given relation R is an equivalence relation or not. So first thing is that reflexive. First requirement is that my relation R should be reflexive. Now what do I mean by reflexive? We'll take example again. A equals to 1, 2, 3, 4, 5. Now R be a relation, and we know that relation is nothing but subset of A cross A. So this will contain coordinate pairs like 1, 1, 1, 2, 1, 5, 2, 2, 2, 4, 2, 5, and so on, elements like this. A relation is said to be reflexive if it contains a regular pair. I'm saying it regular pair. And by regular pair, what do I mean? That my first element and second element both will be same, like this. Addition to this, one more thing is that all the elements 1, 2, 3, 4, 5 and their regular pair should be visible in my relation R. In that case, I'll call my R as reflexive relation. Like if I have 1, 1, 1, 2, 1, 5, 2, 2, 2, 4, 2, 5. So in order to make this relation reflexive, what do I need? I need 3, 3 also. I need 4, 4. I need 5, 5. Means these 5, I'm calling it regular pairs. These 5 regular pairs will be needed. Okay, this is a must condition for the relation to be reflexive. Now if we have A, my set on which we are going to find a relation is A comma B. Now give me a reflexive relation. Simply we can thought of a reflexive relation R, which is nothing but A comma A comma A, regular pair A comma A, B comma B. This is a reflexive. Okay. Adding to this R1, my new relation, this will also be reflexive. The only needed condition to be reflexive is that AA and BB should be there, regular pairs. Number of elements, same number of regular pairs should be visible. Now, if my A is 1, 2, 4, 5, 8, now R equals to 1, 2, 2, 4, 5, 8, 5, 5, 2, 2, 4, 4, 1, 5, 8, 5. Now, this can also be a relation. Clear? We will be looking for the pair 1, 1, regular pair 1, 1. 1, 1 is not visible. So simply by just watching that 1, 1 is not there in this relationship, I can say that R here, R dash is not reflexive. Means corresponding to all the elements of A, the regular pairs should be in R dash. 1, 1 should be there, but it is not there, therefore this is not reflexive. Clear? In terms of general definition, we say reflexive. A relation is reflexive if for every element A, any element A, like here it was 1, 2, 3, 1, 2, 4, 5, 8, any element A, the pair AA should belongs to R. Like here we are searching for 1, 1, because the condition says that for every element A, for this 1, because 1 here belongs to A, so I need 1, 1 to be in this relation, so that makes it relation reflexive. But 1, 1 is not there, so R dash is not reflexive. Clear? Here I have 1 belongs to A, 1, 1 is there, okay, then 2, 2, then 3, 3, then 4, 4, then 5, 5. R is reflexive on the set A. Okay. Now after reflexive, what do we have? After reflexive, we have one more condition, that is called symmetric. A relation is said to be symmetric. Symmetry is like just a pattern, that if we are facing mirror, then our reflection will be symmetric. Clear? So it's nothing but if, remember, reflexive had a condition on the element of set, that A belongs to A, then A comma A should belongs to R. Symmetric and transitive have conditions on relation, that is, if A comma B, any coordinate pair, is in R, then its symmetric image, that is B comma A, should also belongs to R. Okay, like if my R is defined as, I don't know what is my B here, what could be that, but I need the symmetric pairs. These should be there. Clear? So this is my relation which is symmetric. Now, particular case, if A equals to 1, 2, 3, 4 and 5, then observe this. Clearly this is reflexive, no doubt, because regular pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 are there. Is this symmetric? Of course it is symmetric, because 1, 1, the symmetric pair for 1, 1 will be 1, 1 itself. Clear? So this is my reflexive as well as symmetric. If I include just one more element, that is 3, 4, now this is reflexive but not symmetric, because 4, 3 does not belongs to relation R double prime. Clear? So this is reflexive but not symmetric. Clear? Symmetric only means that any ordered pair AB in relation R should have B comma A also as an element of R. This is all what symmetry means. This was my symmetry. Now I can make a proper definition of symmetry. A relation R is said to be symmetric if for a pair AB belonging to that relation R, I must have B comma A belongs to relation R. Only this much. Means if 1 comma 2 is in relation, then 2 comma 1 should be in relation. If 1 comma 3 is in relation R, then 3 comma 1 should be in relation R for every existing pair. Clear? We will do example in the coming videos. Now, this was my second condition in order to make a relation, equivalence relation. What was my third condition? Third condition is called transitive. This is nothing but a transit path, we can say. That if A is related to B and B is related to C, then A must be related to C. In order to understand this, we will first understand that if A is brother of B and B is brother of C, then A is brother of C is obvious thing, because A is brother of B and B is brother of C. This implies that A is brother of C. This is called transitive. Okay. Now in the elementary form, that if I have a pair A comma B belonging to the relation R and I need two pairs, but the condition will be this element will become the first element in the second coordinate pair. Clear? If I have A comma B belonging to R and B comma C belonging to R itself, then I must have A comma C also in the relation R. Like if we look at this R double prime, we have 3 comma 3, 3 comma 4, or we can say that 4 comma 5 also if I include here. Then what do I have? 3 comma 4 belongs to R double prime, 4 comma 5 belongs to R double prime, then 3 comma 5 must also belongs to R double prime in order to make this relation transitive. Clear? So to make it transitive, I must include the pair 3 comma 5. We can make separate examples for these pairs to be transitive. Now equivalence relation. Equivalence relation. Any relation R on a set A is said to be equivalence relation if R is first reflexive, which was nothing but A comma A should belongs to R for every A belonging to the set A on which we are performing the relation. Second condition was symmetry, which was nothing but if A comma B belongs to R, then B comma A should also belongs to R. This was my second condition, symmetry. Third condition, transitive. Transitive was if A comma B belongs to R and B comma C belongs to R, then A comma C should also belongs to R. In this case we say that it is transitive. Now we'll take one example. Okay, let T be the set of all triangles. Of course there are only 4 types of triangle: scalene, equilateral, isosceles and right triangle. Clear? Now we need to check the relation R, which is defined as T1 comma T2, where T1 and T2 are any two triangles in the set T. T1 may be right triangle, T2 may be isosceles, or both may be isosceles, both may be scalene, or T1 may be equilateral triangle, T2 may be right triangle. Clear? Any two triangles T1 comma T2 will belong to relation R only if T1 is congruent to T2. That is, T1 should be congruent to T2. If this condition is satisfied, then we can say my triangles belongs to relation R. Now we need to check whether this is an equivalence relation or not. To make this an equivalence relation, it needs to satisfy 3 conditions, that are reflexive, symmetric and transitive. So we'll check on our first condition, that is reflexive. Now for any triangle T belonging to, say, T1 triangle belonging to the set T, we can make it a little bold like this. Okay, reflexive condition was that for all the elements in the set, the regular pair A comma A must belong to the relation. So if I have some triangle T1 in the set of triangle T, then of course T1 is congruent to itself. Every triangle is congruent to itself. Therefore T1 comma T1 will definitely belongs to R, because every triangle is congruent to itself. So T1 comma T1 will belong to R. Now this will happen for every triangle T, because T1 was arbitrary. Therefore this makes R is reflexive. Okay, ahead of this, what do we have? We need to check the second condition, which is nothing but symmetry. This was my first condition, reflexive. Second condition, symmetry. Now when do we say a relation is symmetric? If we have ordered pair A comma B belonging to the relation R, then B comma A also belongs to that relation R. In case of triangles, what do we say? That any arbitrary ordered pair T1 comma T2 belongs to R. We will suppose this. We will say let T1 comma T2 belongs to R. We have no idea about T1 or T2, what this could be. Okay, but we only know one thing, that if T1 and T2 belongs to R, then T1 is 100% congruent to T2. Otherwise, this ordered pair T1 comma T2 cannot belong to R. Now, if T1 is congruent to T2, then also T2 is congruent to T1. Of course, if one triangle is congruent to other, then we can say that other triangle is also congruent to first triangle. So T2 is congruent to T1. This makes that T2 comma T1 belongs to R. This was my ordered pair which I chose to be in R. Now I inverted that. This is the symmetric image which belongs to R now. So this makes it symmetric. Now my R is symmetric also. Now we are going to check our last condition, which is nothing but transitiveness. So for transitiveness, what do we have? Our relation was R equals to T1 comma T2, such that T1 is congruent to T2, which was subset of set of triangles, cross product of set of triangles. Okay, now we need to check the last condition, which is transitiveness, whether or not my R is transitive. For transitive, what do we need? Let any two ordered pair T1 comma T2 belonging to R and T2 comma T3 belongs to R. To make it transitive, I need to show that the ordered pair T1 comma T3 also belongs to R. That is, if T1 is related to T2 and T2 is related to T3, then T1 must be related with T3. Okay. Now, since T1 and T2 belongs to R and T2 and T3 belongs to R, and the only condition to be in R was that T1 should be congruent to T2 and T2 should be congruent to T3. Now, since T1 is congruent to T2, T2 is congruent to T3, this implies that T1 should be congruent to T3. Okay, because if any two triangles are congruent and these two triangles are congruent, so T1 must be congruent to T3. So if T1 is congruent to T3, then what do we have? That the pair T1 comma T3 must belong to the relation R. Okay, so this makes my relation R transitive, and because now relation R is reflexive, symmetric and transitive all, thus R is an equivalence relation. Now another example. In this example I will be having my set of all the lines. L is my set of all lines in a two-dimensional plane, that is xy plane, and the relation R here is defined as what? Any two lines, this ordered pair means, will belong to the relation R if L1 is perpendicular to L2. We need to check whether this is equivalent relation or not. Now, first condition for equivalence relation is what? Reflexive. One can clearly observe that a line cannot be perpendicular to itself, since L1, a line that belongs to the set L, cannot be perpendicular to itself. Thus, what does this represent? That L1, L1, the regular pair, does not belongs to my relation R. So, if the relation R is not symmetric, then is not reflexive. Yeah, this implies that relation R is not reflexive. So now if it is not reflexive, then how can it be an equivalence relation? So we drop the idea of R being an equivalence relation. R is not an equivalence relation here. But we can show that R is symmetric. And for symmetric, we need to choose an ordered pair in R. So let L1, L2 belongs to R. Thus, condition to be in R is what? L1 is perpendicular to L2, which is same as saying L2 is perpendicular to L1. So L2 is perpendicular to L1. This implies what? That L2, L1, this ordered pair should belong to R. So we took this pair, this is the symmetric image, and this also belongs to R. This makes my relation R symmetric. In the same way, we can check whether it is transitive or not. Okay, so what do you think? Is it transitive or not? Think for 2 seconds. Let's have some break of 2 seconds. Now, we'll go by definition. In order to be transitive, we need to suppose two pairs, L1, L2 in R and L2, L3 in R. This was my supposition. If it is transitive, then I must show that L1, L3 belongs to R. Now, is that possible? That a line L1 is perpendicular to L2 and then L2 is perpendicular to L3, then L1 is perpendicular to L3. This is not possible, because if this is my line L1, then perpendicular line, this is my line L2, because L1, L2 belongs to R. This means what? L1 is perpendicular to L2. So L2, L3 also belongs to R. This makes that my L3 should be perpendicular to L2. So my L3 should be like this. So now can we say that L1 is perpendicular to L2? No. Therefore, thus L1, L3 does not belongs to R, which shows that this relation is not transitive. Means the relation was not reflexive, was not transitive, only symmetric relation. Okay, we can do many examples like this and check whether the relation is equivalence relation or not, or it is reflexive, symmetric, transitive, whatever it satisfies. Okay, now we'll take another example. What do we have? Show that the relation R in the set A, let us suppose that 1, 2, 3 be my set A, and the relation R is given by 1, 1, 2, 2, 3, 3. Observe that this has now already become reflexive because regular pair 1, 1, 2, 2, 3, 3 already are in my relation R. And additional to this, I have 1, 2 and 2, 3. So this is my given relation R. What I have to show that R is reflexive. Already we have discussed, because all the three regular pairs corresponding to 1, 2, 3 are in R. So this is reflexive. Okay. But this relation is not symmetric, not transitive. Okay. So in order to argue about non-symmetry, we need to find a pair 1, 2 in R whose symmetric pair, that is 2, 1, does not belongs to R. We can show 2, 3 also. 2, 3 belongs to R, but 3, 2 does not belongs to R. So this shows that this is not symmetric. Transitive. 1, 2 belongs to R. 2, 3 belongs to R, but 1, 3 does not belongs to R. So not transitive, because 1, 2 belongs to R and 2, 3 also belongs to R, but 1, 3 does not belongs to R. So the relationship here, or we can say just the relation, is not symmetric, not transitive. Okay. Similarly, another example. Now I choose my set of integers where I will find my relation R. This is the set of integer. So R on this is defined as ordered pair AB such that 2 divides A minus B. I need to show that R is equivalence relation. Okay, now let's check whether R is equivalence relation or not. There is no possibility of not equivalence because we already need to prove that this is an equivalence relation. Okay, so whether this is reflexive or not. Of course this is reflexive, because for any or we can say that for every, we can argue with, for every element A in the set of integer, 2 divides A minus A, because this makes it 0. Therefore for every A in Z, A comma A belongs to this R. This makes it reflexive. Symmetry. Let A comma B belongs to the set of integer and to this relation R, and the condition to be in R is what? That 2 divides A minus B. Clear? So we only need to see whether 2 divides the difference of two numbers or not. We don't need to bother about the negativity or positivity. So we can directly say that A minus B equals to 2m, because 2 divides A minus B. So by Euclid lemma we can see that a minus b will be equals to 2m. This is also same as minus of b minus a equals to 2m, which can be written as b minus a equals to 2 times of minus m, and this condition is nothing but 2 divides b minus a. Therefore my relation R is nothing but symmetric. Now the last condition, which is transitive. For that we will choose two pairs, a comma b belongs to R and b comma c. Let us suppose that these two pairs belongs to R. We need to show that a comma c belongs to R. That is, if a is related to b and b is related to c, then a is related to c. Now this condition gives me what? 2 divides a minus b, and this condition gives me what? 2 divides b minus c. This means what? That my a minus b equals to sum 2 times n, and this means what? That my b minus c equals to sum 2 n. Now I need to check whether a minus c is being divided by 2 or not. So I can write a minus c as a minus b plus b minus c. I just add b and subtract b in this. This makes this. Now a minus b was nothing but 2m and b minus c was 2n. This makes it 2m plus n, means a minus c equals to 2m plus n. This will also be an integer, so this shows that 2 divides a minus c. This nothing but a comma c belongs to R, which makes it transitive. R is, and thus R is equivalence relation.